So if we take a look, based on this information, so this is one of those questions that I would attribute to fatigue, because there's a whole bunch of junk here, and as you're reading it, you're already zoned out, right? But if we take a look, it's a 0.125 molar aqueous solution. So that lies between here and here, right? So I think this is actually just reading a graph. So if we take a look, it's between here and here. That means that we should see percent ionization be somewhere between 4.2 and 3.4. And we should see equilibrium being somewhere between 4.2 and 5.1 times 10 to the negative third, respectively. So it has a larger percent ionization, a lower hydronium ion concentration, and lower pH than 1.5. So right there, we can see it should have a larger percent ionization. And this is the one that 5 of you answered yes, and a lower pH. Right here, if we take a look, what is the negative log of this number? That's equal to what? No, I don't need the actual number. I just need to know what it is. The pH. So this right here is going to be higher. So that means that this will actually have a higher pH. I'm sorry, let's say this. It's going to be more acidic, which would mean it would have the lower pH. So this part right here is not correct on that. It has a larger percent ionization and a lower hydronium ion concentration and a higher pOH. Nobody answered for that one. It has a lower percent ionization and a higher pOH than 0.1. So if we take a look here, 0.1 is 4.2%. So we should have a lower percent ionization of that and a higher pOH. Well, a lower pOH is characteristic of a higher, a lower pH is characteristic of a higher what? pOH. So that right there would be true. To tell you the truth, I think this question is junk, and I see, I mean, it's asking you, basically what this is doing is it's asking you to make sure that you understand all of these definitions and stuff more than anything. It does come down to basically being a graph reading exercise as well as check your definitions, right? What might be easier for a test taking technique is to go ahead and scribble on here just some fake percent ionizations. You don't have to know the real one, but if you scribbled some number, let's just go halfway between these two, and then halfway between these two, you could actually maybe pick something that you can calculate the pH of in your head or something like that, and then you can subtract from 14 to get the pOH. But that's the basis of this question. It is a graph reading exercise, so you can sit there and put the 0.125 here, and then extrapolate some ideas of where these should be. And the trends are there. Everything else is just definition. Higher pOH versus pH and stuff like that. The endothermic autoionization of pure water is represented by the chemical equation shown above. The pH of pure water is measured to be 7 at 25 degrees and 6.02 at 100 degrees. Which of the following statement best explains this? It is endothermic because the delta H is positive. So what does that mean? If we increase the temperature, what are we going to favor? Products or reactants? Reactants, and the reactants are the ionization of the hydronium and the hydroxide ion concentration. If we increase the hydrogen ion concentration, the H3O plus, the hydronium, whatever you want to call it, if we increase that, then if we take the negative log of that, it will be less than 7, right? Right. So that's why as you increase the temperature, even though you get a higher hydronium ion concentration, it does affect the pH. So there it is. Yeah, at higher temperatures, dissociates more. And the thing is even though we consider pH 7 to be what we call neutral, if the hydrogen ion or hydronium ion concentration and the hydroxide ion concentration are equal, it's also considered neutral. And that's probably the hard thing there for that. It's not necessarily about pH being 7, it's the hydronium ion equaling the hydroxide ion concentration. Yes. You got it. If you were to sit there, no matter what you do to the temperature wise, if you take H2Os and you sit there and break them apart, did you get this one right? Are you the one? Oh, but yeah. I mean, it's like if you have all of the identical Legos or whatever, and you take off a part, you're always going to have an OH and an H plus if it's talking about water. 7, at higher temperature, water dissociates more. So right there, that's the problem that you had. So the fact that you put greater than here, whenever you see it's a 2 to 1 to 1 mole ratio, if we increase temperature, we are going to increase this and this. So that was the problem there. You should have either chose B or D. Those are the only true possible answers. And then the fact that it is delta H is positive, meaning it's endothermic, you would know that it would not be B. Yeah. Which one was yours, Monk? That's a pretty big one. Perchloric acid. Perchloric acid, strong. You need to have those memorized. So right there, you would know it's between A and B. Looks like a lot of you did not bother doing the antilog the negative log of this, right? What's the negative log of 1 times 10 to the negative 5th? 5. It's just the exponent, right? Why would you want to know that? 8. Okay, all right. So yeah, I'm not sure why 5 of you picked this, other than the fact that you thought strong meant something that it didn't. Strong doesn't necessarily mean that it's going to have a low pH. It means that it ionizes completely. It's all based on that hydrogen ion concentration that tells you what the pH is. Don't fool yourself into a misunderstanding what strong means. You can have a hydrogen, an HCl, a hydrochloric acid concentration. And if you just take one little drop of it, it's not going to all of a sudden go, right? It's not going to drop the pH down to the bottom if you have a very low concentration of it. Even though 100% of it did dissociate. That's the one we did earlier, right? Half and half. Let's see this one, 7. Weak acid. Acetic acid has a pKa of 4.76. The solution is prepared by mixing 500 milliliters of 0.150 molar and 0.020 molar. Which of the following can be used to calculate the pH? So this is a Henderson-Hasselbalch equation. With the 0.02 and the 0.1500, the issue that you're dealing with is the amount of milliliters. It's not 1 liter, and they give you the molarity of the 1.50. You have 500 milliliters of it. So in reality, you're going to have how much? Instead of 0.15, you would have, what's half of that? 0.075. Well, you know that 0.02 is of the NaOH is going to react with 0.075. So what does that end up making the concentration after the hydroxide neutralizes? What's 0.02 from 0.075? 0.055. So that's going to be our acid or our HA, which is going to be on the bottom. And the 0.02 is, since this 0.02 moles of NaOH turned that acid into its conjugate base, that's going to be our A negative, which is on the top of our Henderson-Hasselbalch equation. So there we go. Does that make sense? Should I write something down versus just talking about it? You sure? That would be nice. Okay. Dun, 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 dun. Am I showing my whole screen here? I had too much kolache today. You like kolaches, Emma? Right? Have you ever had the biscuits and gravy one for breakfast? Don't even start. You're too young. Wait till you're old. It's ridiculously good. You have kolaches, Gabe? Yeah, they're pretty amazing.
Are you doing that on my chem?
No, this is just a piece of scrap paper. Where's the thing at? Where's the question? All right, I think that the hardest part of this one is realizing what's going on. So I'm going to go ahead and write up here. We have, and remember, this is a part that you would not be able to use a calculator on, I believe, right? So there's acetic acid. We don't usually write this like this. We usually write it HC2H3O2. However, you have to be aware of both. We're adding this with sodium hydroxide, and that is going to yield C2H3O2. Hopefully that doesn't screw you up too much, but I'm going to cheat a little bit. Just put it into a format that I like to see it, and H2O, right? So what are we starting with? Now here's the problem, is to give you the molarity of that 0.150. That's 0.150 moles per liter. We don't have a liter, we only have how much? We have half a liter. So how many moles do we have then? Half the moles, 0.075. And we have 0.02 moles of this. Remember, sodium hydroxide is a solid, so they could just drop that in there. And again, what are they thinking about the volume? They're not thinking about it because they're considering it to be what? Same, 500 milliliters. We know that's not true, but it's a problem, right? So if we have these two amounts, how much of this is going away? Right. So our limiting reagent here. When this takes away the hydrogen from that, it makes exactly the amount equal to the strong base. So this is our A negative. This is our HA. Henderson-Hasselbalch is pKa plus. Plus log of A minus over HA. So that right there, then we just take this number, put it there, and this number, put it there. Can I do this? Hey, I can do that. Cool.
Can you remind me how you calculate pKa?
pKa is the negative log of the Ka. They actually gave it to you in this problem. But it's the negative log of the acid equilibrium constant.
Okay, thank you.
Yeah, I'm trying to think. It would basically be products over reactants, right? The Ka would be the products over the reactants. Same problem. Yeah. Same problem. pH versus volume data for the titration of 0.10 molar nitrous acid. So that's a weak acid with 0.10 molar potassium hydroxide plotted above. Potassium hydroxide, strong base. This is based on the data, which of the following species is present in the greatest concentration after 6 milliliters. What does the base do to this? What does the base do to HNO3, HNO2? It takes away what? The H. So let's take a look here. HNO2 plus potassium hydroxide yields H2O plus NO2 negative. Right? So 6 milliliters is here. The actual point of neutralization or the equivalence point is 10. So what's half of that? 5. We are at 6 milliliters, so we are above 5. Remember, there's a few things that we could get from this data. Half of the equivalence point should be the pKa. So 5 right here. If we were to go over here, that would be the pKa. That's not what this question is asking. It wants to know which is in the greatest concentration. We are past halfway. So does that mean our H pluses are in high concentration or not? Those are what are going away, right? But at this point, as they go away, we get lower concentration of H pluses. So that's not going to be it. HNO2 is the nitrous acid. What's happening to the nitrous acid as we titrate? It's going away. We're getting NO2 negative instead of HNO2. When is the HNO2 its highest? At the start. When is the H plus at its highest? At the start, even though this is not a strong thing, but it's not going to dissociate completely. But as it does get pulled out, more and more is going to dissociate, right? That's that whole equilibrium thing. So we know it's not A or B. OH negative, as soon as we drop OH negative in there, what's happening to it? It's reacting with who? H plus to form H2O, right? So the only one that makes sense is us pulling this hydrogen off of here, producing more NO2. Since we're past half point, that means we're going to have more of that NO2 because we pulled off what from it? All the H's. Yeah, if you want some less thinking, more sentences that directly answer, yes, that is good. Monk said, so past a halfway point, you have more of the conjugate base, and that is true. And Monk said he doesn't talk like that. La 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 la. 0.20 molar solution of weak acid potassium. That's KHP. 0.10 based on the titration curve above. The pKa is closest to what? So what is this? We're at the 10 point. So what's half of 10? 5. So the pKa is, if we look at 5 milliliters, where is this on the graph here? The pKa is equal to the pH at the halfway point, right? Is this it? More electronegative, hydrogen and bromine. Bromine. So the 3 bromines on this carbon are going to do what to these electrons overall? Pull them this way. That means that it's going to be easier to take which one of these hydrogens? One on bottom. There we go, right? Acid 2 is stronger because it's more stable conjugate base than acid 1 due to the greater number of electronegative bromine atoms. Some people put this, acid 1 is stronger. If you put that, you really need to review your ideas of what Ka is, right? Which of these is closer to 0? Number 2, so what does that tell us? That the products are favored more for number 2, right? So that tells us that this one is more acidic because it's more likely to give up the H. So if you were one of these guys, make sure you recheck that Ka thing. And then these guys right here, more polarizable molecule with stronger intermolecular forces. Sounds like gobbledygook. More polarizable molecule with stronger intermolecular forces. I get you on that. It's one of those garbage ones where which one is the better answer, right? Stronger intermolecular forces. Yeah. Reading this one, I mean, I just think that you'd have to skip over that one, like, because it's not really answering this question. D is definitely the better answer. What did they say? Did they say anything about YC? No, they just reword what D says, right? These two acids differ in the substitution of one hydrogen atom by a more electronegative bromine atom, making a condiment. All right. Same thing. Tellurium versus selenium. Which one has more electronegativity? What's that? Closer to fluorine, right? Selenium. So if we take a look, H2Te, tellurium is less electronegative, resulting in less stable conjugate base. Same thing. This is interesting. What's Ka1 versus Ka2? What does that mean? Yeah, there's 2 hydrogens, right? So each one would be able to pull off. So this is the Ka of one of these hydrogens. Since they're identical, it doesn't matter. This is much greater than 1, so that must be pretty decent strength-wise. What's that? Well, for like HCl and stuff like that, sure. To tell you the truth, that's actually why I was taken aback by it, because what is this even called? This is some acid I've never dealt with. Do they even have a name for it? They're like diprotic oxide, oxyacids. It makes sense, but yeah, right. To tell you the truth, this Ka being greater than 1, it's not one of our common strong acids, but depending on how much greater than 1 it is, then this may actually be a strong acid. I've never dealt with this acid before in my life. First time I saw it right there. Fun for this. NF3 is weaker because the greater electronegativity of F compared to H. Is it considered a strong one? Huh. But yeah, we would never deal with it. So you have to basically remember what your Lewis acid bases are. A Lewis base is an electron pair donor. So if all of these Fs are sitting here, like the electrons from that nitrogen, is it going to be able to give them away easily? No. But the hydrogens are like, you do your thing, nitrogen, with your electrons, right? Yeah. Go Bay or whatever. But so those are going to be able to be pulled off easier for sure. Yes. Is it? It's not one of the 6 common yet. Cool. That's what I figured by looking at the Ka. Yeah. Everybody did good on this. Everybody did good on that. Yeah. The weak acid ionization equilibrium for blah is 3% student measures blah, 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 using a probe pH meter as experimental setup based on the information which PK is 4.25, pH is 3.55. We are dealing with a weak acid based on the information which the following is true. Okay, so this is one where you have to read all these. So 3 people thought that this is stronger than this. Would that make sense with the pH being this low? That the conjugate base is, I'm sorry, that the, if we take a look, this is it losing the H pluses. If it doesn't have the H pluses if they're in solution, then that means it's going to be higher since the pKa of the weak acid is less than the pKw. pKa of the weak acid is less than pKw. Let's take a look at this. This is greater than this since the pKa of the acid is greater than the pH. So if, again, this is one of those things where we have to think about the Henderson-Hasselbalch equation. Let's do this. Can we do this in our head? This right here is on the bottom, and this right here is on the top. And the pKa is greater than the pH. Let's check the other ones to see if anything. pKb is less than pKw. This again is one where it's basically having you compare these two things and making sure that you understand these definitions. But basically, if we just look at the Henderson-Hasselbalch equation, we know that if it's a 1-to-1 ratio, the pH equals what? pKa, right? So if these two are equal to each other, the pH and the pKa would be equal. If we have more of the acid than the base, than the conjugate base, then that means that we are going to be lower in pH. If we have more of the conjugate base than the acid, that means we will be higher in the pKa. In this case, we are lower. So this one does not matter. It's between the pKa and the pH. If you know that this is just between looking at the pKa and the pH, then you got it. And that's what they say. pH is less than pKa if there's higher concentration of the acid versus the base. It's the same type as before. Basically, you have 0.1 mole of this and 0.3 mole of this. What does that mean? That NaOH is going to do what to the concentration of the CH3COOH? They love that. What are those 0.1 moles are going to do to the 0.3 moles? We have 1 liter this time. What's going to happen to 0.3? It's going to become 0.2 because 0.1 mole is going to react with it, canceling it out. So that means we have 0.2 of the acid and 0.1 of the conjugate base. So that's the math right there. Yeah, that's the key. Like if you answered this and it looks like the majority did, you forgot that this is going to react with this and take away 0.1 of this. They like these type of problems. The acid ionization, this is again where you're going to get question fatigue. I'm already fatigued by it. Acid ionization equilibrium for nitrous acid is represented by the equation of blah, 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 blah. 250 milliliters of buffer solution prepared by mixing blah, blah, blah. To test the buffer capacity, the pH is measured and recorded in data. One sample the mixture of the buffer and HCl, which is following best explains why the pH of sample 4 is lower than the pH of the other substance. It is lower. pH of this one is lower. Did they say 4? Sample 4 is lower than the pH of the other samples containing any buffer. Do you know why this one's lower? Because we have 1 drop of HCl in there. Why is 4 lower than 3.26, 3.25, and 3.25? Why is it 3.21? Well, we have to read all of these choices. Prior to measuring the pH sample 4, some water evaporated, resulting in an increase in concentration of the HNO2. That doesn't seem feasible. Water evaporated? It doesn't occur that quickly. After measuring the pH of the more acidic sample 3, the pH probe was not rinsed and wiped. Yeah. I mean, if that's the case, right? If they did not rinse the pH probe after measuring this one with the HCl in it, that would definitely make it lower. Prior to measuring the pH of sample 4, the room temperature dropped suddenly. Yeah. The volume used to measure pH of sample 4 was less than 25 milliliters, resulting in a case concentration. No. Even if that was the case, we still have the same ratio if we allowed it to dissolve completely. Let's see what they say. The best example is pH probe was not rinsed, right? And residue from the more acidic sample 3 lowered the pH. That makes sense. Trying to think, if the room temperature drops slowly, that would favor the reverse reaction, which would not increase the hydrogen ion concentration. Prior to measuring it, some water evaporated, resulting in, even if this water evaporated, our ratios are still going to be the same, aren't they? Remember, we said that if you can either do it by molarity or you can do it by mole to mole in the Henderson-Hasselbalch equation, correct? So even if some water evaporates, it's not going to affect that ratio. The ratio is what's important on that. That's why we were able to change the ratio to use less of the chemical in the laboratory. As long as we maintain the same ratio, we were able to lower the amount of chemicals that we use. We knew that that was going to affect our buffer, and I think it may have affected Dylan's group's buffer, its ability a lot more than others. Did you ever figure out anything on that? No. It's up until Monday. That's all I got. If you didn't do it, I'll reopen it. How do I reopen it? Let them lose 15 points, right? Are we enabling these? Are any of these people that are missing this, are they in contention to like beat you in some type of top 25 competition? Or does that stuff even matter this year? No. They'll never beat me. Any questions from our home audience? The Zoomers. No?
So you are reopening it?
Yes, Creedon, I will reopen it. I need to quit.
Thank you.
You guys are lucky I talked to Mr. Grop. This is like Grop stuff. This is what he would do. This is not usually me. I'm supposed to be the mean one. You can get out of here and have a good day if you want. Versus watching me struggle trying to open this thing. Why can't I do this? This is like $25, dude. Yeah.
all